Hello, welcome back. We're going to talk about some more of the topics in Chapter 5. When we left off, we were going to start looking at the mechanisms of hydrohalogenation. And we're going to notice that some of these steps that are encompassed in this reaction actually are in those common patterns that we described in the beginning of the chapter. You will see that if you understand these mechanisms, that a lot of the memorization in organic chemistry is cut down. Understanding is the key to success in organic chemistry. So let's start. I'm going to share my iPad, and then we're going to look at the mechanism of hydrohalogenation. So when we look at this, I have a two-step mechanism. And the first step is going to be adding a proton. So if I look at this molecule down here, this is symmetrical. So I have one hydrogen here, and I have one hydrogen here. The group is a methyl, the group is a methyl. So I don't have to worry about regiochemistry. I don't have to worry about Markovnikov's rule in this particular example. Here, I just want you to start looking at the mechanism, which is how the electrons move. So I'm going to write this out. And I am going to pick the trans, but it doesn't matter if it's cis or trans. All that matters is that this double bond is a nucleophile, right? So this is a nucleophile, which means it's electron rich. And then the HCl, this is partial positive, this is partial negative. Let me put in my lone pair. So I actually have that dipole pulling. So this is the electrophile, and this is going to be electron poor. My arrow always starts where I have the electron density. So in the nucleophile, the area of electron density, and it goes towards the electrophilic piece. So these two electrons, so it's starting at the bond and it's coming out and attacking that hydrogen. Well, then these electrons are going to come out and end up on the atom, on the chlorine. And what I'm going to get then is I have this CH3, CH, attached to this carbon. Here's my new bond to the hydrogen. I still have the CH3 and I have the H. I also have that chlorine negative, and I only have 3 groups to this carbon, so this is a positive charge. Remember, these electrons that are coming out end up here, and these electrons end up here. So I have an electron deficient species now. This is now going to be something that's electrophilic, and this is going to be something that's a nucleophile, because this now is electron rich and that is electron poor. So this is the first step. I form a positive carbocation. This is a secondary carbocation because the carbon that has the positive charge is attached to 2 groups and 2 carbon groups and a hydrogen. I can also have primary and tertiary carbocations. And it's really important what type of carbocation is formed, whether it's primary, secondary, or tertiary, because there's a notable stability difference in those types of carbocations, and that influences the mechanism greatly. So we'll talk about that in a little bit. So the first step is going to be a nucleophilic attack of these electrons, the pi electrons and the double bond on the hydrogen, and then the chlorine is going to leave. The chlorine, that bond is going to break, and those electrons are going to end up on the chlorine. So that sets me up for the second reaction. So in the second reaction, what I'm going to have is the electrophile that was formed. That's going to be my carbocation. And the nucleophile, which is the Cl minus, are going to react to form a new covalent bond. So remember what's going to happen here. I'm going to draw this out just again. This is my positive charge. So my chlorine, with all of its electron density, right, this is going to be the nucleophile or the lowest Lewis base because it actually has an electron pair that it can donate. The cation, the carbocation, is going to be a Lewis acid because it wants those electrons. It wants to accept an electron pair. It's an electrophile. So this is electron rich. This is electron poor. My arrow is going to originate from the electron rich species. And basically what I'm going to have is an attack on that carbocation by the chlorine, which forms this new bond. So now I have the final product, reaction of that carbocation with that chloride ion is going to complete the reaction. Now, I can monitor this reaction and describe this reaction with an energy diagram. This is going to be a two-step mechanism. So remember, I'm going to have two pumps on my diagram. So I'm going to have two transition states. I'm going to have two different energies of activation. This is my intermediate, which is going to be my carbocation. This is going to be my rate determining step because this is the largest energy of activation. And then this is my energy of the products. This is the energy of the reactants. Those products are lower in energy than the reactants, which means it's exothermic and energy is given off. So overall, it's exothermic because my products are lower in energy than the reactants. And this is what I would consider to be step one, which is formation of the carbocation. And then step two is that formation of the new bond. And this is how I am going to describe this reaction. Now, I might give you a reaction like this and say, draw an energy diagram that describes this reaction. And then you would need to come up with something like this, knowing that it's two steps, knowing that the formation of the carbocation is usually the rate determining step, and then the reaction of the intermediate is going to be much faster, knowing that it has those two transition states and the two activation energies. Now, it doesn't have to be exothermic. My products could be higher in energy than the reactants. It just depends on the type of reaction. So this one is definitely exothermic. All right, so let's look at carbocations. This is the tert-butyl cation. So let's look at that. I have my carbon that has the positive charge. This carbon is going to be sp2 hybridized. and it is going to be trigonal planar. So it's flat, and my bond angles are going to be 120 degrees. Remember, this is flat. What I have is this vacant 2p orbital in my sp2 hybridized carbon. Now remember, this carbon is sp3 tetrahedral. This one is sp3 tetrahedral. And then this one is sp3 tetrahedral. So those sigma bonds, these sigma bonds that are formed by overlap of sp2 to sp3 hybrid orbitals. This is vacant. There is no, there are no electrons in that p orbital. Those electrons that were part of the double bond, if I think about the reaction on the previous slide, left to form a new bond. So now I have this vacant p orbital, which makes it that perfect Lewis acid. It's ready to accept a lone pair from something else. So carbocations are going to be a species containing a carbon atom that has 3 bonds to it. It only has 6 electrons and it bears a positive charge. So it's a carbon that has a positive charge. The bond angles are going to be about 120. I have the sp2 hybrid orbitals that form that sigma bond. That unhybridized p orbital is perpendicular to the sigma bond framework, and it's empty. It contains no electrons. Remember, carbocations are electrophiles because they're electron loving. They're electron poor. They're electron deficient. You could use all kinds of terminologies for something that's electrophilic. And they're also Lewis acids because they want to accept an electron pair in order to complete the octet. Now, this knowledge about carbocations is going to give us a lot of information in this chapter, but also for future chapters. Because of this, remember, I have this flat trigonal planar array. So the atoms that are attached to that carbon and the carbon that bears the positive charge are all in the same plane. That's a flat system. That's going to have some ramifications later when we start talking about stereochemistry and other things that will be important as we go through our mechanisms now and in the future. I can have various types of carbocations. Now, you want these carbocations actually are going to correspond to, remember we had tertiary alcohols, tertiary amines. When I have a carbocation and I have 3 carbon groups attached to that, that is going to be tertiary. When I have the carbocation and I have 2 carbon groups attached to it, that's going to be secondary. When I have carbocation and I have 1 carbon and the rest are hydrogens, that will be primary. And then my methyl carbocation is just when I have a methyl group that lost a hydrogen and became positive. Now this is really important. This is, I'm going to highlight this. This is the order of increasing carbocation stability, which means that the tertiary carbocation is more stable than the secondary, and it has a lower activation energy for its formation. It's easier to form a tertiary carbocation than it is to form a secondary carbocation. And in turn, secondary carbocations are more stable than primary, and it will require a lower activation energy for its formation. Methyl and primary carbocations are very unstable, so much so that they're almost never observed in solution. So this is a very important order of reactivity. Tertiary carbocations are much more stable than secondary, which are much more stable than primary, which basically is more stable than methyl. These are very unstable, and this is very stable, relatively speaking. The secondary is somewhere in between. But I have this order of reactivity, which helps us to explain things like Markovnikov's rule. Now, you might ask, why are my tertiary carbocations more stabilized than my primary and my methyl? And that's because of this inductive effect that we spoke about in terms of acid-base chemistry when we used our Rio to determine the acid strength of organic molecules. I have this polarization of that electron density in a covalent bond, which is a result of the high electronegativity of a nearby atom. The electronegativity of a carbon atom, right? My carbon atom bearing a positive charge is very electron withdrawing inductive effect. So it's going to pull electrons towards it. It's going to polarize electrons in adjacent sigma bonds. That positive charge is not then localized on that carbon. It's delocalized over nearby atoms as well. The larger the area over which that positive charge is delocalized, the greater the stability. Alkyl groups are electron donating. So they're going to donate electrons to this positive charge in order to stabilize that positive charge. They're going to sort of accept this delocalization and increase the stability. Hydrogen can't do that as well. So the more carbon groups that are attached, the more stable the carbocation that's formed. So when I think about this, my tertiary carbocations are more stable, and they will have a lower activation energy, which means that they form quickly, right? Secondary carbocations are next in terms of the order of, or the stability. So let's look at these. When I have these methyl groups, those methyl groups actually donate electron density towards that positively charged carbocation carbon. And that delocalizes that positive charge. That delocalization results in a stable ion. Hydrogen can't do that, right? If you look at this electrostatic potential map, this center of blue is where I have a really high positive charge. That carbon is very positive and it's localized. Notice in this one, that blue is spread out. It's not as intense right around that carbon. So that positive charge here is delocalized. And it's delocalized because these other carbon atoms are actually going to stabilize. They're electron donating. They donate electrons to this positive charge. This is how we sort of designate that, where those are going to be donating electrons, which stabilizes the positive charge. This is much more stable than this. So this is much more stable because of the stabilization. This is very unstable because of that localization. So let's look at this in the terms of the reaction mechanism for the hydrohalogenation. This actually explains Markovnikov's rule. If I can understand the chemical basis, I can understand these reaction mechanisms, and I don't have to memorize Markovnikov's rule. Markovnikov's rule makes sense. So the chemical basis, right? The reason that Markovnikov's rule is actually observed is because of these relative stabilities of these carbocation intermediates. These relative stabilities are critical for explaining Markovnikov's rule, right? So this regioselectivity is going to be explained using Markovnikov's rule. So let's look at this. If I have propene, so I'm going to draw this out. I have two pathways. I have this pathway and I have this pathway. I can either add the hydrogen. I'm gonna go, let's see. I am gonna add the hydrogen this direction. So what I get let me make that bond more clear. What I get there is this carbocation. And notice I have two carbon groups attached. So this is a secondary carbocation. The other way I can go is if I have my HCl in this direction. So if it goes this way, what I'm going to get is this carbocation. So I have two different ways that this hydrogen can add when I consider that either of those carbons of that double bond can receive that hydrogen. This is a primary carbocation. That is this guy here. That's primary. It's primary is much less stable than secondary. Secondary carbocations are more stable than primary, right? So I have two outcomes that are possible. The carbon is going to form, either one of these carbons is going to form a bond to hydrogen. So if it's this one, I'm going to get this. No, if it's this one, I'm going to get this guy here. And then if the hydrogen goes to this carbon, then I'm going to get this guy here. And that is my secondary carbocation. Notice this is not formed, and that's because I do not form this carbocation. The primary carbocation does not form. So this entire pathway is wrong. I can always form two carbocations from my double bond. This is carbocation number 1. This is carbocation number 2. That is because, do my electrons swing out the orange way or do they swing out the green way? If I look at the reaction mechanism and I look at the 2 intermediates that could potentially be formed by the addition of hydrogen both ways, I can clearly see that this is a more stable carbocation, right? This is very unstable. So this is going to predominate, and this one is not going to form because of those differences in stability. So this is the product that I actually get, and I don't get the other product. The other product is not observed. Okay, we're gonna take a break here, and then what we're gonna do is look at some of these other reactions. So when we get back together, we're gonna start looking at hydration and some of the other reactions in this particular section. All right, I'll be back.